Ever stop to think about how our gadgets, the phones in our pockets, the laptops, even those massive AI systems, how they keep getting faster and more capable?
It definitely feels like magic sometimes, doesn't it? But it's really about relentless engineering.
Exactly. Welcome to the deep dive. Today, we're going to get into that by looking at semiconductor fabrication, specifically how nano manufacturing is changing the game for the chips that power, well, everything.
Yeah, we've got a really interesting case study here. It's from a leading semiconductor company, and it digs into how they tackled the real roadblocks in traditional lithography.
Lithography. That's basically printing the circuits onto the silicon. Right?
Pretty much, yeah. So our mission for this deep dive is to understand how these super advanced nanomanufacturing techniques let them make chips smaller, faster, and crucially more energy efficient.
And hopefully we can do that without needing, a PhD in electrical engineering.
That's the plan. Keep it clear, keep it focused on what matters.
Right. So this company, they hit a wall with the old ways of making transistors smaller. What was the core problem there? What were they really up against?
The case study makes it clear that traditional lithography, that projection and etching process we mentioned, was just hitting its physical limits, like
They
fundamental,
couldn't shrink things down anymore.
not with the precision they needed. It became incredibly difficult to create those super small transistors for the next generation of microprocessors.
Hmm.
The required detail just wasn't achievable reliably.
And that limitation wasn't just academic, right? It had real-world consequences for technology.
Oh, absolutely. It directly slowed down how small the transistors could get. And smaller transistors are key, right? They switch faster, use less power.
So hitting that wall meant slower progress in computing speed.
And energy efficiency, yeah.
Yeah.
Which holds back progress in really demanding areas.
Areas like AI, which needs massive processing power,
Yeah.
and edge computing, high-performance servers,
Yeah.
all that stuff relies on better chips.
Exactly. The demand is just constantly growing.
So how did this company plan to sort of leapfrog those limitations? What was their big strategic move?
Well, the case study shows a really decisive shift towards nanomanufacturing techniques. The core idea is getting control down to the atomic level.
Atomic level precision. Wow.
Yeah, manipulating materials and processes with just incredible accuracy. The goal was basically to keep Moore's law going.
Ah, Moore's law. Good old Moore's law. For anyone listening, that's the observation that the number of transistors you can fit on a chip roughly doubles every couple of years. It's driven decades of progress.
And it wanted to keep that engine chugging along even when traditional methods were stalling. So they needed new tools, new techniques.
Okay, so what were some of these specific nano manufacturing techniques they brought in?
Right, several key ones. The first really big one mentioned is extreme ultraviolet lithography, EUV.
EUV sounds very high tech. What does that actually let them do that the old way couldn't?
It uses light, but with a much, much shorter wavelength than traditional methods. You can think of it like swapping a thick marker for an ultrafine pen.
A much finer paintbrush for drawing those circuit patterns.
Exactly. And that lets them create patterns on the silicon wafer at a drastically smaller scale. We're talking features smaller than 5 nanometers.
Sub 5 nanometers, it's hard to even picture. A human hair is what, tens of thousands of nanometers wide?
It's mind-bendingly small, yeah. And the payoff is huge.
Okay, what's the payoff?
A really significant increase in computational power. The chips can just do more faster. And they also managed a reduction in power consumption.
Faster and more efficient. Plus, I think the case study mentioned it simplified things too.
It did, yeah.
Yeah.
Using EUV actually allowed them to streamline production. They could get rid of some really complex multi-step patterning processes that they used to need just to try and get those tiny features. Made things a bit more efficient on the manufacturing side, too.
Okay, so EUV is like this super precise light beam. What was the next piece of the puzzle?
The next key technique was atomic layer deposition, ALD.
ALD. What does that involve?
Imagine building something up, but depositing the material just one single layer of atoms at a time.
Yeah.
Perfectly uniform, incredibly thin films.
One atomic layer
Uh,
at a time. The control must be just phenomenal.
it is. And the benefit for transistors is much better control over the gate.
The gate being the switch that controls the electricity flow.
Exactly. With ALD, they could build those gate structures with amazing precision. This led directly to less current leakage, less wasted electricity.
Which means better efficiency again.
And it also improved the chip's overall reliability. Better electrical properties, fewer tiny defects that could cause problems down the line.
Less leakage. More reliable. Makes sense. Were there other techniques involved?
Yep, they also used advanced nano-patterning methods,
Yeah.
specifically something called self-assembly, using block copolymers.
Self-assembly sounds like the materials build themselves.
It's kind of like that, yeah. It's a really clever technique where these specialized molecules are designed to spontaneously arrange themselves into the exact, highly regular patterns needed for transistors at the nanoscale.
Wow. So you're guiding materials to create these incredible uniform structures almost automatically.
Precisely, and the result is you can pack circuits even more densely onto the chip without losing accuracy.
And more density usually means.
Faster processing speeds and, again, better energy efficiency. It all ties together.
So you've got EUV for the fine patterns, ALD for the precise layers, nano patterning for density.
Mm.
But even with all this control working at the atomic scale, there must still be a risk of tiny flaws, right?
Yeah.
Imperfections.
Oh, absolutely. Making billions of transistors perfectly every time is, well, it's basically impossible. And that's where the fourth key element comes in: AI-powered quality control.
Using artificial intelligence for QC, how does that work?
They integrated AI systems designed specifically to detect defects, even incredibly small ones, at that atomic scale. These systems analyze huge amounts of data coming off the production line in real time.
So the AI is looking for tiny mistakes as they happen.
Exactly. Identifying and flagging imperfections much faster and more accurately than humans ever could. This allows them to catch problems early, make adjustments, and reduce the number of faulty chips.
That sounds like a massive advantage. Reducing waste must be huge.
It really is. The case study highlights a significant drop in yield losses. That's the percentage of chips that don't pass quality checks. Better yields, more reliable chips overall.
Okay, so implementing all these techniques, EUV, ALD, nano patterning, AIQC, it sounds like it really paid off. Did the case study quantify the improvements?
It did. They reported a 20% reduction in defect rates after rolling out these nano manufacturing processes.
20%, that's substantial.
Huge. And it had knock-on effects, right? Higher
Yeah.
production efficiency, less wasted material, which means lower manufacturing costs, and just more consistent quality in the final chips.
Makes sense. What about the actual performance of the chips? Did end users see a difference?
The performance benchmarks were pretty impressive. Compared to the previous generation, the new microprocessors showed a 30% increase in computational speed.
30% faster.
And on top of that, a 15% reduction in power consumption.
Faster and uses less battery or electricity. That's the dream combination, isn't it?
Absolutely. And numbers like that really position the company at the forefront, especially for those demanding markets like AI, data centers, high-end mobile devices.
I bet their customers were happy. Did the tech firms using these chips notice?
Oh yeah. This study mentions widespread adoption by leading tech companies. They also picked up quite a bit of industry recognition, awards, and such for pushing the boundaries of semiconductor fabrication. Really cemented their reputation as innovators.
It sounds like they didn't just make incremental improvements either. The case study talks about some major client achievements enabled by this.
Definitely. One of the biggest highlights was the successful development of 3-nanometer transistor technology.
3 nanometers. We were talking sub 5 nanometer earlier, now down to 3 nanometer. That's another huge leap.
It really is. It's enabling even more powerful, even more efficient devices. It's directly extending that Moore's Law curve we talked about.
Pushing the boundaries of physics, practically. What did achieving that 3 nanometer capability mean for the company and the market?
Well, it gave them a significant first-mover advantage in this ultra-advanced fabrication space.
Being the first ones there.
Exactly.
Yeah.
And that allowed them to secure some very lucrative, high-value contracts with the biggest names in tech. It significantly boosted their global market share and gave them a real, sustainable, competitive edge.
So mastering these techniques wasn't just about the tech, it was a major business win.
Absolutely. Market leadership followed the technological leadership.
And you mentioned efficiency gains earlier. Did the case study touch on sustainability or environmental aspects as well?
It did, yeah. That's an important angle. These optimized nano manufacturing processes, because they were more precise and efficient, also led to reductions in raw material usage and energy consumption during manufacturing.
So better for the bottom line and better for the environment.
Kind of a win-win. It helps with financial sustainability, obviously lower operational costs, but it also aligns with the growing push across the industry for more environmentally responsible manufacturing, less waste, lower energy footprint.
So pulling it all together, this deep dive into the case study really shows that nanomanufacturing isn't just about making things smaller.
No, it's more fundamental than that. It's about unlocking new levels of performance, radically improving energy efficiency, and finding more sustainable ways to build the hardware that underpins our digital world.
These atomic level techniques are really driving the future of computing.
They absolutely are. The precision is just incredible.
It really makes you think, doesn't it? As these techniques get even more sophisticated, moving beyond semiconductors, what other fields could be totally revolutionized by this kind of atomic level engineering? Where else could this precision take us?
That's a fascinating question. Material science, medicine, energy.
Hmm.
The potential applications are vast. It'll be exciting to see what comes next.
Definitely something to keep an eye on. Well, that brings us to the end of this deep dive. Thanks for exploring this with us.